Hello, I'm Kristen Wegner, and I'm delighted to welcome you to today's webinar, Climate Proxies, What We Know, How We Know It, and How to Communicate It to the General Public. Climate Voices is a collaboration of the University Corporation for Atmospheric Research and the United Nations Foundation. Climate Voices is a network of over 400 climate science experts across the country that volunteer to speak with their fellow citizens about climate science, climate change, and possible solutions to this immense challenge. Our webinars are designed to provide our scientists with tools and tips for public engagements. This webinar is made possible through the support of the National Science Foundation's Division of Atmospheric and Geospace Sciences Paleoclimate program. We have a really exciting panel today. We're joined by Dr. Jonathan Overpeck, Dr. Julie Cole, and Dr. Kim Cobb. For each of our presenters, we'll have about 12 minutes to present, and as we go through the presentations, you can type your questions and comments into the chat window at any time. You could also tweet them using @climate_voices, and I'll ask the questions as I can throughout the session. At the end of the presentations, we'll also have time for discussion. So I'm pleased to present our first presenter, Peck. Peck is a founding co-director of the Institute of the Environment and Thomas R. Brown Distinguished Professor of Science at the University of Arizona. He's co-PI of the Climate Assessment for the Southwest Project, CLIMAS, and the University Director for the Southwest Climate Science Center. He's a coordinating lead author for the IPCC, the Fourth Assessment, and has been awarded the U.S. Department of Commerce Bronze and Gold Medals, the Walter Orr Roberts Award of the AMS. He was also a Guggenheim Fellow, AAAS Fellow, and AGU Fellow. He commits significant time at the interface between science and society, both to help promote understanding of science, as well as to help scientists understand broader views, particularly those of decision makers in society who must deal with real-world climate variability and change. Welcome, Peck.
Thanks. So could I have the next slide, please? A little technical. I'm waiting for the next slide, but it's a pleasure to talk with all of you. Normally, when I'm giving a presentation, to a faith group or a community group or out here in Arizona, a lot of times it's a retirement community. What I'm trying to do, or stakeholders, is I'm trying to figure out a way to get a good hook on what they're interested in. And of course, usually that has to do with the water situation out west, or sea level rise in places they know and love elsewhere around the country, or why are the forests here undergoing bigger and bigger wildfires and just outright tree death as we get these record hot temperatures. And I try to bring in paleo where I can to inform that whole issue that is most relevant to the group I'm talking to. But what I'm doing today, next slide please, is I'm going to just try and talk a little more about how we use paleo. And I wrote a paper a long time ago on the paleo perspectives, and so I'm using that term. And they include all sorts of archives, and here you can just see trees, foraminifera, lake sediments, and someone in our National Ice Core lab with a big chunk of polar ice. Next slide, please. There are, of course, a lot more types of proxy information, and I think Julie's going to show you what I think is a really effective way to sort of connect that with the audience. What I wanted to sort of give this overview of the kinds of things I usually bring paleo into, the story that I'm telling, or the talk, to give them a better understanding of their natural world and what's ahead. The first thing is paleo provides a full range of past environmental variability and change. You know, when we look at the instrumental record, it's just a very small subset of 100 years, and the satellite record's even shorter. But with the paleo record, we can go back centuries, millennia, even longer. Another thing when you start doing that is you start to see climate system behavior that you've never seen before. And, you know, of course, some of the most famous are, you know, what happened at the Cretaceous Tertiary boundary when the dinosaurs went extinct. It involved climate, believe it or not, when the asteroid hit the planet. But there are a lot of other smaller surprises that, if they were to occur today, would really wreak havoc on our society and natural systems. We also need the paleo perspective because we're really pushing this climate system with large forcing change. Change in greenhouse gases in the atmosphere is really going to create a change that's on the scale, potentially, of a glacial interglacial cycle. And yet the instrumental record doesn't contain that level of change. We want to see how the climate system is affected by a big change in forcing like it might get in the future. And when we're talking about the future, almost all of our colleagues are using modeled projections of the future or assessments. And everyone's interested in the public about, well, how good are these models? You know, you can't even forecast the weather 2 weeks out from now. How can we trust a model, a projection of 100 years from now? And so, you know, you talk about how weather and climate are different and do that whole bit, but it really helps you to show examples of how well these models are able to simulate ancient climates, which these days is pretty darn good. And the last thing is detecting and attributing anthropogenic change. There are a lot of ways we can contribute to that with paleo evidence. So I'm going to give you a couple examples in the time I have, and then, of course, I'm sure you'll get more from Kim and Julie. Here's just a case of looking at air bubbles trapped in polar ice from Antarctica, just giving you a sense of what the natural envelope of CO2 variation has been over the last 800,000 years. You know, that's the length of the longest ice core we now have from Antarctica. And these are just samples of past atmospheres, and you can see that naturally the CO2 levels in the atmosphere have never gone, over the last million years almost, above 300 parts per million. And if you see that on the far right-hand side, there's that green line across the top, we're up to 400 now. We pretty much have gone through 400, it'll never go below in any of our lifetimes. And you can just see very viscerally or visually how clear the change is that we humans have caused relative to natural variation. We're way outside the natural envelope of variation. Next slide, please. And this is, you know, from the IPCC. I forgot to put the attribution on it, from the 5th Assessment Working Group 1 report, the Paleo Chapter 5, just showing now reconstructed Northern Hemisphere temperature for the last 2,000 years. And it's kind of an ugly graph, I know. And I could have shown a simpler one. And I got to admit, for this presentation, I didn't spend a lot of time finding the ideal graph, but rather I want to make points. And the point of this slide is that on the far left-hand side, the most recent period, in black, you can see the instrumental record. Temperatures are just soaring now. And, you know, 2014, 15, now 16, all breaking records in a row for the warmest on the instrumental record. But you can see all these wiggly lines are the different reconstructions based on different proxy data. Some cases trees, sometimes other proxies being brought in, showing the reconstructed temperature for the last 2,000 years. And it's often very powerful to show that really the last couple of decades are unusual, unprecedented in the last at least 1,300 years, perhaps even longer. And of course, as we go back further in time, it gets a little harder to say that. But now we can say with some confidence that the temperatures we're getting on this planet, the Northern Hemisphere globally, are unprecedented in many centuries. And like with the CO2, that really makes clear how big the change is that humans are causing with their emissions of greenhouse gases. Next slide, please. And I wanted to just sort of tie this in. That what we're looking at in this slide is that same, not quite the same interval time. We're going back about 1,200 years. And the MCA is the medieval climate anomaly. The LIA is the Little Ice Age. And of course, the 20th century is on the far right. The gray shading depicts the observations of temperature in the Northern Hemisphere over this time and the uncertainty. The darker the gray, the more certain that was the temperature back in time. And so you can clearly see that during medieval times, the Northern Hemisphere appeared to be a little warmer. It wasn't uniformly globally warmer, but in the Northern Hemisphere, average it was. Cooled down in the Little Ice Age, and then we got this big warming coming up recently, and that's the so-called hockey stick. But the red and blue lines demark the sort of the uncertainty in model simulations of climate over the same interval of time. And what I think is remarkable now, for over 10 years, we've been able to simulate the climate of the last 1,000 years pretty well within the estimates, the air estimates of our understanding of what that climate really was, in this case temperature. And what we know is that if you can, using reconstructions of past volcanic eruptions, solar irradiance, and greenhouse gases, you can pretty much simulate the climate of the last 1,000 years. And if you didn't have the greenhouse gases in there, you wouldn't be able to simulate the most recent warming. So this is a very powerful way of showing not only are these models pretty darn sophisticated now, they are also incapable. Our understanding, we cannot simulate or explain the current warming without the greenhouse gases. So that's important for attribution as well. Next slide, please. And this just shows the last glacial maximum period about 21,000 years ago, and we have lots of data both from ocean on the lower left and on land on the right. And the dots in both cases are the actual data, and the simulations are the continuous color fields of both SST in the lower left and surface air temperature on the upper right. And the reason I like the last glacial maximum, because it was globally 3 to almost 6 degrees C colder than today, and it reflects sort of the same scale of change that we're likely to get in the future if we don't curb greenhouse gas emissions. And here we can see, if you have good eyes, that we do a pretty darn good job of getting the magnitude of the change right with our climate models. And this is an average, those fields, of many models, so it's a multi-model ensemble, seems to do pretty well in reconstructing the last glacial maximum. Very powerful to say these models are able to do that scale of climate change. A little on the proxies. This just shows how we calibrate some of our proxies. The maps I just showed, the observations of sea surface temperature reconstructed 21,000 years ago, are based on in many cases, geochemistry of planktonic foraminifera, and this just shows how well we can do that. There's scatter, but in a sense we're looking at a plot of magnesium, calcium versus temperature that's reflected for each of those samples in modern samples. And it gives us a lot of faith that our reconstruction methods are pretty darn good. And we have multiple proxies, so we can always be checking one approach to reconstruction versus another. Next slide, please. We're wrapping up now. I wanted to wrap up on this last one, just talking about a surprise. And there are a lot of surprises in the paleo record that could occur in the future, and that if they did would really not just be, oh my gosh, it would really have big effects on our economy and natural systems. What I'd like to talk about is the last interglacial period. So this is about 125 to 130,000 years ago. And what was interesting about this period, it's simulated in this map by climate models that match pretty well with observations, is that it was about half a degree warmer than today. Okay, and you can see there's amplification in the high latitudes, just like it's going on now with global warming. But not the whole world wasn't warmer. What's interesting about this, so it's just a little warmer than today. Okay, what's the big deal about just a little warmer than today? Next slide, please. Well, global sea level during this period of time was 4 to 9 meters above present. Okay, so we're about a half degree warmer than now, and sea level is 4 to 9 meters. We're talking 20, 30 feet of sea level rise. Okay, with just a little warmer. Next slide, please. The question is, where did that sea level rise come from? And a lot of our paleo colleagues have worked on this, and including a paper we wrote a number of years ago showing that only a fraction of this could come from the expanding ocean as it warmed and from the Greenland ice sheets. Some of this big sea level rise we had at this time had to come from somewhere else, and everyone who's listening probably has done the math. It had to be Antarctica. Next slide. And there's a recent paper, Rob DeCanto, Dave Pollard came out with a great paper in Nature trying to simulate this with a new climate model of the coupled ice sheet. And here's the view of the ice sheet that may have existed with just a little greater warmth than we have today. And you can see most of the West Antarctic ice sheet is missing, and large swaths of the East Antarctic ice sheet are now exposed. Now we just have land, the brown in that map. Just giving you a sense that just a little more warming could really disintegrate an ice sheet, multiple ice sheets. And that's the kind of power that paleoclimatology brings to the table. We probably never would have known this had we not had these wonderful ice core records, marine sediment records, and understanding of how ice sheet and sea level interact. And I think that's my last slide. Thanks.
Great, thank you. That's very comprehensive, and I could see a lot of our participants using those resources for their public presentations. I'm pleased now to introduce our second presenter, Julie Cole. Julie leads a research group at University of Arizona that emphasizes climate and environmental change on human timescales in systems with large societal impact. She uses paleo data to provide a deeper perspective on phenomena such as El Nino, drought, reef environments, and monsoon systems. She is dedicated to communicating climate science and is an Aldo Leopold Leadership Fellow, a Google Science Communication Fellow, and held the Udall Center Fellowship in Environmental Policy. Thank you, Julie.
Thanks. Next slide, please. So paleoclimatology is really well suited to communicating climate science to a public audience, and for a number of reasons. One of those reasons is, as Peck described, that it really directly addresses a lot of questions that people will walk into the room having. So for example, how do we know these models are any good, right? Or what do we really know about how much climate can change? Can we really change climate? How much has climate changed? Paleoclimatology is the only way that we have observed climate to be changing. So it's a unique set of windows on past climate that tells us that, in fact, the climate that we see for the last 50 to 100 years through our historical experience and instrumental records is really not a unique solution to the climates that can exist on Earth. And in fact, there are many different ways that climate can change very, very strongly. So we have observations, not just computer programs that say this could happen, but observations of those kinds of changes happening. So that's really cool as well. We can use them to test the climate models that we use to simulate the future, because those climate models are developed with the modern system in mind. And what if they're kind of stuck in the modern? What if they can't simulate the past? I think Peck showed nicely how we've used climate models in conjunction with paleo data to address that question. Finally, as well, paleoclimate data give us a context for the current extremes that we're seeing increasingly. And I'm going to talk a little bit about that in the context of drought in the Southwest. So that's one reason that paleoclimate data are really a powerful approach. But I want to mention another one too, which is that paleoclimatology is kind of fun. You know, here we are in the, here we are in the Galapagos on scuba using power tools underwater to get cores out of a 200-year-old coral so that we can understand more about El Nino. This is fun. This is actually a still of a movie. I didn't want to subject you to the whole thing, but really these kinds of visuals, including video, are things that get people's attention when you're talking to the public. And they're the kind of things that you can find online, or if you have a particular thing that you want to see and you put out a request to somebody like Kim or I or anybody else, Peck, who takes pictures in the field, we can provide you with these kinds of visuals. And there's sources of those through the NOAA Paleoclimatology website as well. So, so this is something that appeals to people, right? We get out and use power tools underwater. We have a quest going on when we go out in the field. We're looking for that, it's not like we go underwater and there's a whole field of 500-year corals that we take our pick from. It's really a quest to find the best samples and to understand those samples well enough that we can get a climate record out of what's essentially a piece of rock. I actually have an example. It's not from the core you see being drilled there, but here's the kind of thing that we take out of a coral underwater. It's a core, and a core might be 2 meters in length, but of course we take it out in pieces because it's very awkward to handle a 6-foot long core. We take a slab out of the middle, and that's where our samples come from. But this is another way that you can connect with audiences, is if you bring in a visual, something like this, and say, this coral grew, in some cases you might say 4,000 or 5,000 years ago. This particular one happened to grow up until about 2015 when we sampled it, so it's fairly young. But we have all kinds of samples that we bring back from the field that we can show which have some wow factor. There's a coral from Ecuador. Here's a cave sample from Ecuador. We might be able to say, look, this is 10,000 years old, and there's a record of 10,000 years of climate in these little bands here. So that's something that we do a lot of, is to show these kinds of samples. And that's a powerful communication tool. So if you have access to a paleoclimatologist near where you're giving your talk, I suggest that you ask to borrow some visuals because that can be a very powerful tool to connect. All right, next slide. Why are we drilling this coral in Galapagos? Well, and why does 200 years of record qualify as a climate record? I mean, that's not really that old in geological time scales. But in fact, you'd be surprised at how limited the instrumental record actually is. This is a map showing the mean number of ocean surface temperature observations per month in a commonly used database of ocean surface temperature. This is for the mid-20th century, 2 decades there, 1930 to 1950. And as you can see, the tropical Pacific is pretty depauperate in actual climate observations with thermometers over this interval. An average of less than 1 observation per month, and those long streaky bits of color that run through the Pacific, there are ship tracks, meaning that the observations you do see were likely taken on maybe a single cruise during that period, but they might have taken 20 in 1 month, you know. So the observations are scarce, poorly distributed, before about the late 20th century in parts of the world that we really care about. That blue box is the area over which NOAA defines the state of the El Nino system. So it's really important to be sampling in these areas that cover important climate systems. And those are the kinds of things that Kim and I and Peck spend a lot of time thinking about. Where can we get the best samples that tell us the most about large-scale climate change? And we're learning a tremendous amount about how this particular system, El Nino, has changed through time. One of the big lessons is it's got a lot of natural internal variability. But another lesson seems that over centuries to millennia, it goes through periods where it may be weaker or its impact on the global climate may be much weaker. And that's a picture that's becoming clearer and clearer through work like what Kim is probably going to talk about and some work that we've been doing in Galapagos as well. Next slide. Next slide, please. So one of the cool things about paleoclimatology is, as I said, these are observations that we have of past climate. This is a core from a lake in Galapagos, and you can see that the top is nice brown mucky sediment, and then, you know, about halfway down it suddenly turns red and then white. Well, something big happened there. Now, we just took this core about a month ago, so we don't know exactly what happened, but based on some previous work that we've done there, we're pretty sure that that's a big dry period. So we'll find out more about that. But it's a little bit of a mystery story, and at the same time, there's clear evidence that anyone can see, looking at it, of course, that something has changed. Next slide, please. And here we are hunting down fossil corals in a sea of black lava rocks, where we're coring a coral here that, again, we don't quite know how old it is, but so there's a mystery to this as well, but we'll find out soon enough with dating. Next slide, please. Now, I described this like it's all really, really easy to do, and of course paleoclimatology is not a hobby, it's a science, and one of the things that we struggle with is how to interpret our records properly in terms of past climate change. Not just saying that the sediment went from brown to red, but actually saying what that means in terms of climate. So we spend a lot of time trying to show how we know what we know, as the title of our webinar here suggests. And one of the things we spend a lot of time on is calibration. Here we're in a cave. This is a former graduate student of mine, Sarah Truby, operating a calibration station that collects both water samples and modern cave carbonate, which we can measure and compare those measurements to climate data and to the measurements we get from the stalagmites that grow in the cave, to say something about how we know what we know about paleoclimatology. There's a tremendous literature on that. And again, people who are expert in those particular areas can direct you to that literature or explain to you how to best interpret some of these records that are coming out. Next slide, please. All right, I want to talk a little bit about how a particular area of interest here in the Southwest has been dealt with in paleoclimate terms. And as Peck mentioned, you know, knowing your audience and what they care about in terms of climate is super important. So here in the Southwest, water gets a lot more traction than climate change, right? So talking about water and drought is a more effective strategy for getting people to think about the kinds of environmental changes that they're experiencing. And of course, over the last few years, we've seen major drought in California that is really only the tail end, well, maybe it's not the tail end, but it's the most recent manifestation, let's say, of a drought that's been going on here in the Southwest since about 1999, coincidentally the year that I moved here, so that's sort of sad, but hopefully we'll get to see the end of that drought as well as the beginning. Next slide, please. One of the most effective ways to look at past drought here in the Southwest has been to look at tree ring-based records, and this is just an example, again, something that's very visual that you can use to show how tree growth varies from year to year. There are thick bands and thin bands, and it's a pretty easy thing to describe how a tree will grow better under climate conditions that are more favorable for it. And again, here in the Southwest, usually the favorability is related to water. Next slide. So a number of people are applying tree ring data to look at the most recent anomalies that we are seeing here in the West and try to place those in context. One of the striking features of the last few years in California has been the absolute lack of snow cover in places that are usually well covered by snow throughout many months of the year. We are seeing on satellite images that the snow cover has really diminished, and so you can correlate tree growth with snow cover using clever statistical methods. And a group led by Valerie Touré's group and Balmacheri et al. Here at a paper recently published in Nature, I believe, shows that the snow cover reconstructed for 2015 is actually the lowest value over the last 500 years. Lowest by a hair, but you can see that there are about 5 previous intervals where the values were comparably low, but only about maybe 5 intervals in 500 years. So a pretty rare event, and this past drought is the worst in that record. Next slide, please. Looking at a little bit longer perspective and reconstructing precipitation, here's a 2,000+ year reconstruction of precipitation in northwest New Mexico, an area that's been hard hit by drought since 1999. Up until the last 20 years or so, we think that the 1950s drought was one of the strongest on record. And the top set of curves here, the top curve here shows that drought reconstructed in the tree ring data and labeled there. But you can see that if you take a 2,000-year perspective, the 1950s drought is nothing but a small blip on top of much stronger and longer-lived droughts that have happened in the past. So that's useful information. Those, by the way, caused by natural, internal, or maybe external, but natural causes. Next slide, please. Branching out from records like that into a more regional perspective, this is from a data set by Ed Cook and others that was assembled looking at drought across the West. And what we're seeing is a measure here of the percent of the western U.S. that is experiencing drought from 800 AD to about 2000. And what we see when we look at that broader perspective is that there have been intervals in the past where we had a much more arid, generally arid climate, in particular between about 900 and 1300 AD. And trying to understand what's behind that and what caused that is a major focus of research for all of us, I think, who are participating here. As well, you see some intervals that were wetter. So the tree rings give you this two-way picture of drought and wetness over a much longer interval than we could possibly hope to obtain otherwise. Next, please. All right. Finally, applying that long-term perspective to think about the future, in a paper by Ben Cook et al. That just came out, we're looking here now at that tree ring-based reconstruction in the brown that goes from about 1,000 to 20. This plot goes up to 2,100. Okay. Obviously, we don't have future tree rings, but if we calculate the drought index for the Southwest from tree rings and then calculate a drought index from climate models and stitch that on the end, what we can see is even those periods of prolonged extreme drought, which we would call a mega drought in the past, are dwarfed by what we might expect in the future from climate models that simulate both temperature and precipitation and their influence on moisture availability in the soil. So this paleoclimate record tells us that, yes, Mother Nature is capable of some pretty wild behavior, but our climate models suggest that we may be pushing that system even beyond what we've seen in the past during these periods of prolonged and intense drought. Thank you. Next. So just to wrap up, I think that one of the powers of paleoclimatology in terms of its communication appropriateness is just to couch it in terms of trying to solve the mysteries of past climate and understand those causes, because they are really important to trying to understand what the future might hold and how we might think about that in the context of what we're experiencing now and in the past. Next, this really is a quest. And we're often setting out to do it under fairly, strenuous conditions. We're all carrying big packs here off to find some lakes in Galapagos here. But it's the kind of story that you can craft into an effective communication device to tell a story of searching for something and finding it. So I think that's what I have found personally to be an effective way to talk about climate change. Thanks.
Great. Fantastic. I really appreciate the elements of story and also the quest, as well as knowing your audience and crafting a message to that. So thank you. So I'm now delighted to introduce our third presenter, Kim Cobb. Kim is Associate Professor in the School of Earth and Atmospheric Sciences at the Georgia Institute of Technology. Her research uses corals and cave stalagmites to reconstruct tropical Pacific temperature and rainfall patterns over the last decades to millennia. She's sailed on 6 oceanographic cruises and led 5 caving expeditions to the rainforests of Borneo in support of her research. You may have seen her on the Emmy-awarded TV show Years of Living Dangerously, and she'll now discuss the power of communicating climate change impacts through personal experiences, including the challenges and benefits. Welcome.
Thanks a lot. Thanks for having me. And thanks to all of you, by the way, for your passion in communicating climate science. I think one of the things we would all agree with is that it can be somewhat daunting and a little scary to enter the fray with climate change communication, but I really commend everybody who is determined to hone their skills in this area and to get out there and start talking about this, because it is something that we should all take personally as a kind of a call. So thank you, first of all. And great to be here. And I wanted to talk kind of obviously leaping off where Julie left off about corals and how we can understand climate extremes of the past and put some context to what's happening today. But I'm going to take a little bit more of a personal tack here and recognizing that while Julie said paleoclimate is not a hobby, it's a science, of course I agree with that, but I would also go so far as to say that paleoclimate is not a hobby, it's a way of life. And that quest aspect and that personal drive and dedication, persistence that it takes to extract higher and higher quality records from particular sites over basically in my case 20 years of dedicated research. And then obviously to think that you know what you want out of your site and then to have it happen and then to have a very humbling experience when that goes down. That's a personal story I wanted to bring to bear about what has been a 20-year quest. So this is research that has been going on since 1997, which many of you will recognize was the last major El Nino event that took over our planet in the media back in the day, and of course that has been supplanted heartily by the most recent event in 2015-2016. And this has been work that many students have been involved with, as well as longtime collaborators, and pretty consistently funded by NSF and NOAA, so I'd like to acknowledge them right off the bat too, and I'm going to talk today about. Next slide. So this is how I open my talks to the public, my favorite side of our planet. This is the Great Pacific Ocean, and next slide. And this is my research site in the middle of that Great Basin. So it kind of really hits home for me, of course, the importance of our oceans in determining not only the climate change question, but of course the fate of our planet as a whole. So this is just to orient them for communicating the passion that I feel when I think about the fate of our planet, in particular the fate of my very microscopic research site in the middle of this big basin. Next slide. And so this is where my career began. So I've been hunting El Nino events in corals for my entire life at this particular site in a very dogged obsession trying to figure out how to deliver the best records and provide the most elusive of constraints about changes in El Nino extremes. And this was my first research cruise in 1997. Back in the day, we actually had a very bad prediction of that particular event, and so we found ourselves floating around in 3 or 4 degrees C warm anomalies in the middle of the Central Pacific, and it wasn't a pretty cruise, but it was really inspiring for me to realize how powerful this was and how little we knew about it. Next slide. Fast forward to this year, of course, now we have media declaring the Godzilla El Nino of the millennium, perhaps in hindsight a touch of hyperbole, but I would argue not so much if you're a coral. We have really profound challenges in understanding the evolution of El Ninos under climate change, and most specifically recognizing that they are in many cases the straw on top of a camel's back of climate change for particular ecosystems that are particularly threatened by warmer ocean temperatures. And you know, in climate science we often think about anomaly this and anomaly that, but for corals they really care about absolute temperature. And so that's a really, I think, important thing to drive home about the nature of climate change and translating it to the public to make sure that we appreciate that some of these things are going to be thresholding type impacts. That are going to be cascading and ever more severe, even if the phenomenon itself as a magnitude anomaly doesn't change. Next slide. So I am very fond of framing paleoclimate in this particular way. We'd really like to understand this question about change in the extremes. These extremes, by definition, don't happen every year. Well, unless you're in the western U.S. drought, in which case they are happening every year. But many of the most dire climate extremes don't occur every year. And so we have two options in front of us. We can wait 100+ years until we have amassed enough instrumental observations of these extremes and how they're evolving with greenhouse gases. Or, of course, next slide. We can turn to paleoclimate records to quantify, and I really want to stress that word for many people in the audience. You know, we have really moved way past, as Julie said, kind of, you know, geologists with rock hammers going around and chasing things, although I fancy myself a geologist with a rock hammer who can wield it pretty well. I also fancy myself a person who's equipped with data analysis tools, capable of digesting model output, and comparing it quantitatively to my data, and really bringing a new level of rigor in conjunction with people like Julie and Peck and a whole generation of us who have grown up with much more kind of quantitative training than many of the past paleoclimate people. So we can quantify past variations in climate, including climate extremes, from these particular records. And this is, of course, you know, I think our best hope of understanding the changes in climate extremes by extracting this information from the paleoclimate record and using it quantitatively. And next slide. So obviously, Julie has already talked about corals quite a bit, and these are just pictures of my favorite ugly corals. Of course, we can extract, as Julie pointed out, records of maybe a century or two off the living reef via scuba and power tools. And if we want to push that further back, we're relegated to these kind of older corals that are long dead, lying around on beaches. And at Christmas Island, where I work in the middle of the Pacific, we've been pushing this back 7,000 years through much of the current interglacial period. And we date these with uranium-thorium dating techniques, and we apply the exact same kind of proxy analysis to these older corals to create an apples-to-apples comparison of how El Nino is behaving in the past to how it's behaving today. Next slide. And so this is something that we can do quantitatively, and I think it's important to stress that for corals, I think we have a fairly good understanding of how they record climate, and that's in part because they're very easy to calibrate because they grow so quickly and they extend across much of the instrumental record. And so we are capable of assessing how well a given record does. And so corals accrete as a function of sea surface temperature, which is a thermodynamic effect on the coral skeleton as it grows, and then also changes in the oxygen isotopic content of seawater, which is largely related to changes in salinity. It's kind of a close relative of salinity in terms of the dynamical drivers. So that is a very kind of great recipe for the public to understand how sea surface temperature is recorded in corals, and that we're really not looking at changes in growth rates or some of these other maybe more qualitative metrics of how climate is recorded. In this case, the coral skeleton can be analyzed for its geochemistry, its oxygen isotopic geochemistry in this case, that we can directly relate to sea surface temperature. And so next slide. Yeah, then the next one. Okay, so this is 20 years of my life plotted on a single plot here. So this is our calibration over the last 30, well, I guess 40 years now. Time keeps going by, record keeps getting longer. But we have, I think, 8 corals plotted on this calibration curve, and what is hard for you to see is that there's a gray curve on there, which is sea surface temperature from largely from satellites in this particular region, given that we have, as Julie mentioned, we have so few instrumental observations, even in this era, prior to the installation of Toga Tau array. And so once we're able to combine many, many different kinds of records onto this calibration curve, this plot through time, then we can really begin to understand exactly how well these corals are recording sea surface temperature. And they're really almost interchangeable with the instrumental record of sea surface temperature from this particular region. So when you show this to the public or to other scientists who are not familiar with paleoclimate data, they kind of say, wow, that's pretty impressive. I definitely would like to see those records further and further and further back in time. They get a clear sense that this is a really high fidelity archive, especially when you have a lot of records to pile together, witnesses to climate change, if you will. Next slide. And so this is one such example of going back in time. These are these pieces now, whereas before I showed you the modern corals, now I'm going to the fossil corals, and I'm looking at uranium thorium dated sequences over the last 1,200 years or so, and there aren't very many of them, and there are very many gaps. This is from one particular island of the 3 or 4 that I've been working across, and so I'm trying to remain in the same apples-to-apples comparison. So these are Christmas Island modern corals on the far right, and then Christmas Island fossil corals. So they should be comparable in terms of the magnitudes of variations that we see. And what you can see here is that well, you can't really see it on this plot, but I'm showing you the value for the 2015-2016 El Nino event that we extracted from corals that were drilled this very spring that grew across the peak of the 2015-2016 El Nino. And they bumped up to that minus 5.5 level in our oxygen isotopes, which on this plot clearly looks quite anomalous. And so while this is a place we know precious little about in terms of either instrumental records or even in paleoclimate records, this is information that tells us just how strange it is today and just how unprecedented this level of warming is today. And of course that's going to translate into pretty devastating reef effects that I'll discuss in a second. So this is, I think, an important communication piece. This is a little bit more complex communication piece. I don't want to dwell on this, but this is basically us looking over 7,000 years of fossil coral information now. So of course we're going back in time, so the modern corals would be at 0 years before present, and the older ones would be at 7,000 on this axis. And so what we're plotting on the y-axis is the relative change in El Nino recorded in these different fossil corals through time. Each of these has been dated. In this case, I'm combining records across 3 different islands to try to get enough data to say something, because as Julie pointed out, one of our primary observations is that this varies a lot, and this is a paradigm that we're beginning to appreciate with respect to paleoclimate perspectives, that there's a lot of variation. When you begin to look in detail through time, you see quite a bit of extremes going on, whether it's drought or pluvial events that Julie was referring to, or extremes in El Nino, like the kinds of variations that I'm plotting here. But one thing that I do feel is worth mentioning that's been emerging from this collective 20 years of work from these research sites is that the level of modern El Nino variability captured in the modern coral records over the last decades is significantly higher than that recorded in sum total, in aggregate, if you will, of the pre-industrial records that we have to date. And so in 2013, I published a paper in Science that kind of flirted with this conclusion pretty tenuously at that point. You have to remember that we were coming off one of the weakest and most boring El Nino periods ever. So I think we were very cautious in what we were saying at that point, and we had far less data than we do now. So fast forward to this year, of course, we're on the heels of a 2015-2016 massive event, which we tacked on to the end of our modern record of data, and as well we've amassed hundreds of additional years of coral information from new sequences by my student Pam Groth. So we're going on to like a 95% level of confidence now in stating that there has been a statistically significant change in El Nino strength from the pre-industrial to today, with an inference for a strengthening of the El Nino Southern Oscillation with anthropogenic greenhouse gas forcing. And that, of course, is a striking conclusion in the face of the coral bleaching from this year. Next slide. So yeah, this is just to drive this point home, and this drives it home for me personally in a way that I could never have predicted as somebody who has been obsessed with these particular research sites for 20 years, working this coral archive. Literally, you know, my mass spec here at Georgia Tech runs 24 hours a day, 7 days a week, crunching coral to extend these records further back in time to lower the uncertainties as to what we can say that happened back in time and what's happening today. And, you know, since 1997 till this year, it had been a pretty boring time out in the middle of the Pacific Ocean. This reef had been growing and recovering from the 97-98 event. I had been watching with my own eyes, much as I watch my little babies grow up right now. I have 4 such babies, so I'm good at watching things grow, and it has been a true pleasure and love to have been so intimately tied to this reef for 20 years. Of course, this year with the El Nino event reaching bleaching threshold at this site, over a period of 9 months of bleaching level temperature stress. We were out there in November. We witnessed wide-scale bleaching, and of course we were there to instrument the reef. We weren't there to document bleaching. But nonetheless, while we were diving, instrumenting the reef, taking some photos and videos, and just being staggered at the ongoing impacts, knowing that additional 5 or 6 months were still to come. And then, of course, we go back in April, and we witnessed 85% mortality of the reef that you can see there on the right. And I documented this in a climate.gov blog that you can check out, kind of how that impacted me personally, how it's probably going to impact my research agenda going forward. It kind of can't not in a way. And I think that this is something that the public sees as largely out of sight, out of mind over there in Australia, but bringing this home in the sense of what's happening to our reefs today and how climate change is impacting this, and how this becomes a perfect example in this particular case of how we combine a paleoclimate perspective to understand the history of modern day extremes for El Niños and put some context around that, and then deliver an example of a reef that is very, very far away being decimated. So it's a personal story for me, but I think it's also a very compelling example of a particular climate change impact and its relevance today. Thank you.
Great. Thanks so much, Kim. I really appreciated that you are that you connected it to the personal and then also to your life. I think that really helps audiences, and so thanks for modeling that. Please type in any questions that you have into the chat window, and I'll moderate it for our panel. But after, I'll kick off with the first question. What advice do you have for the participants in this webinar? A lot of our participants are climate voices, participants that volunteer to go out and communicate to the general public. So advice, perhaps any challenges or reflections that you have throughout your career also communicating climate change to the public. So who'd like to kick it off?
I'll take a start just to, I think at a pretty high level. I started by thanking these people for their engagement, but one of the most important things that I always get at the end of my public talks is, are we doomed? And this is something that as climate scientists, we need to answer that question. It's a really challenging question for climate scientists. It's not a space we think about very often, but really, bringing some personal reflection to that as well. How does it make you feel? What is your perspective on this as a climate scientist? I think that's just a very engaging and very important, honest, very impactful interaction that you can have with an audience. So that would be my 2 cents of something that I've gleaned over the years that Peck and Julie may have others.
If I could follow up on that, I agree. We get that question a lot. Sometimes it's phrased as, what can we do?
Yes.
Because they're worried that there's nothing they can do. And I often have to do my homework a little bit before I go into giving a talk about what's being done and what are good examples of progress that's being made. There are people who are really good at this, and I look at Susan Hassel as a really great example of somebody who's able to find and use good examples of how energy efficiency isn't that hard and how renewables are capable of filling in gaps that they're not filling in now. And so I think it's important as communicators to do your homework about solutions before you go in, because it's so easy, especially as a climate scientist who's spent decades documenting a problem, right? the story can't stop there, because then people get discouraged and they think there's nothing they can do. So it really has to go into the realm of solutions and what can be done. And you know, I was happy today to see in my email my monthly statement for our solar panels that we put on our house about a year ago. And you know, looking at the days of high and low, and you know, what are we doing that makes us net producers or net users on a given day? And I find that if we can come up with examples of how you can benefit, how you can change small things to benefit the climate problem, and how people are doing that. For example, energy efficiency standards in California are a great example of a reduction in greenhouse gas production that's come around pretty painlessly. You know, you don't see their economy in the dumps from new energy efficiency standards. So so we need to find positive examples.
Yeah, and of course, you know, it is very important. I agree with both of these guys about how we can't just say we're doomed. We have a big choice, you know, and it's not just putting solar panels on our roof, it's which is a good thing, and what you can afford to do is a good thing. Mm-hmm. But really comes down to, as a nation, acting on climate change. And so we can't be scared to say, you know, if you feel climate change is something that you shouldn't happen, you know, you vote, and you have friends who vote. And what we're trying to make clear to everyone is that the science is well established. You know, these climate models that are projecting these really large changes in the future, much larger than we've seen, ones that are already bleaching corals, well, they're going to get a lot worse. And the models we know from paleoclimate work are capable of simulating changes in temperature very well. So the big choice is whether we want it to continue, whether you really want your children and their children to inherit a much changed planet. And ultimately, we all have to vote, and we all have to start working harder to reduce greenhouse gas emissions if we don't want it.
Can I add one more point that often comes up? There's a sense among people who may not know a lot about climate is it's really complicated, and scientists don't really agree about what's going on. And I think nothing could be further from the truth, right? This has been looked at so many ways, and you know, the number that keeps coming up is that in the high 90% range there is vast scientific agreement among climate scientists on why climate is warming, that climate is warming, that it's probably not going to be good, right? It's going to be bad. And you know, so there's some basic things that we can point to that there's vast scientific agreement on, and I think that helps people realize that it's not so complicated. I've seen this play out in a public audience where one person in the audience who seems to know what he or she is talking about will stand up and say, well, isn't it true that plants put out more CO2 than humans? Just say the answer yes or no. Or, you know, things like that, and they command a level of attention in the audience that needs to be diffused with a statement about what scientists do actually know and believe, and the basis for that. So,
and when
if we challenge that, you're not speaking to that person maybe, but you're speaking to the rest of the room and saying, no, scientists agree that we are the problem.
And we're the ones who, you know, need to take the high ground and respect the other people in the room. But at the same time, Julie's absolutely right. I mean, when I go into any talk, you know, at this point I give so many public presentations, I sort of know the stuff off the top of my head, but go to Skeptical Science, go to realclimate.org, go to all the websites that are available now so that you are ready to debunk in very clear terms every one of these climate myths that these guys like to bring up. And just about every presentation I give, there'll be someone in the audience who wants to try what Julie just described. And it really is very effective if you can just embarrass them by being nice, but you know, you just clarify the science.
Yeah, I was just going to add one more layer up there, is that, you know, during the so-called hiatus, there was a lot of this kind of in-depth digestion of what was going on, and some uncertainties that were pretty derailing potentially for public audiences. And I think since 2015, 2016 now, you know, I think it's more easy as a climate scientist to just pivot and say, really, I think most of us in this room would agree that we have a problem with this, and kind of just bring it back to some solution spaces, bring it back to choices. I think that's becoming easier and easier as climate change unfolds, especially with the pace that it currently is at. We're breaking records right and left. So that's a kind of a brave new world in the one sense, but I think it does in itself diffuse a lot of the kind of heated rhetoric that had come to dictate a lot of our interactions over the last decade, for example.
Great.
Running out of arguments.
Oh, go ahead, Julie.
I just said they're running out of arguments, you know.
Yes, exactly. I mean, the well is running pretty dry.
And the more that we have resources like skeptical science that scientists and climate science communicators can also use, and I like hearing that each of you also mentioned just preparing and having that be part of the presentation, and also using that as a pivot into a different point also, so that's great. Let's see. We have a question from the audience. Are you concerned about appearing to be an advocate rather than a scientist when you talk about solutions? And then another similar question is, what types of solutions do you talk about, especially with your friends and family, if that gets into the conversation also?
So I guess I'll take a first pass. I'll try to be super quick. I know we're low on time, but I do very much get concerned about the advocacy piece. Frankly, less and less as I move on in my career and as climate change moves on so aggressively, and it becomes really clear that in my personal view, if climate scientists step aside in the interest of maintaining some objective stance on this, the world will lose, and it will lose big. So I've made this choice. Having said that, I just want to illustrate two things. What I do talk about, for the first time this year, I came out and publicly endorsed Citizens Climate Lobby, which for those of you who aren't aware of that organization, it has a website, they have thousands of members, they storm DC every year, banging on doors to talk about pricing carbon. I think they have a great solution, and I'm proud to endorse them publicly now, but this is the first year, and it's that dire. That's why I went there, so that I've struggled with that particular endorsement, for example. I'm over it. The other example I give is through work in my class, where I work on a carbon reduction challenge, illustrating how 30 students can, over the course of a semester, erase their annual carbon footprint as the average American. So I kind of give these big picture policy solution spaces, and then I give something that's very close to home, that's very concrete and tangible, echoing much of what Julie said about the gains of efficiency. You can save money, you can save energy, you can save carbon. Let's do this.
You know, and I admire Kim, I admire Jim Hansen, who goes even further in the advocacy. I don't think there's anything wrong with it. It's just pretty important, though, to be clear where the science is and ends, and where the advocacy begins. I personally am a less of an advocate, but if I'm an advocate for anything, it's for advocate for science and sound science, and that's what leads me to be pretty aggressive with people who are trying to confuse the public on the science. I think that's unethical, to be honest. And I know many people who ask those questions are not being unethical, they're just being curious and they've heard these things. And in those cases, I really feel we have to treat them with utmost respect because they just want to find out what's going on. But when it comes to the end of my presentations, after everyone's pretty bummed out in the room because it made clear what's at stake, I think it's important to show that there are solutions. And ultimately, it's us as a society that has to decide where we go with those solutions. I also am very happy to talk about what I've done. This is going to your question of you know, personally. And Julie mentions the solar panels on the roof. We have a Prius that is ancient, but you know, it doesn't get the gas mileage of the current Priuses. But you know, when you look at the life cycle, I'm pretty proud showing up in the ancient Prius. But at the same time, you know, I live in the West. I got to be able to drive on, you know, four-wheel drive roads and snow, and yeah, I have a four-wheel drive vehicle too. But I choose where I can to have a smaller carbon footprint, and everyone has to choose for themselves whether they find these acceptable or not. In the Southwest, I also like to highlight what happens to us if we run out of water. You know, we have a paper that's getting close to publication now that just agrees with a whole host of other papers that suggests climate change is literally going to dry up the Southwest. And what is that going to mean to our home values? What's it going to mean to those who have their retirement tied up in their mortgage or in their house? Don't shy away from these things, because you have to make it connected viscerally to everyone so they understand what truly is at stake. But ultimately, I'm not telling anyone what to do. I'm just suggesting they really read up on the options.
Mm-hmm. Yeah, I mean, I'm passionate about the need for action. That said, I don't go out and wear that on my sleeve when I give a public talk, in part because I want people to listen to me, and I feel like if I go out as an advocate, that's not who they invited. So I try to keep it to the science in a public presentation, but when people start to talk about solutions, yeah, you know, we need to solve this one way or the other. The thing that I often come back to, and again, it's because we're in a very red state here, and often we're talking to retirement groups or retirement learning groups where we know that there's a real diversity of opinion in the room. And what I try to do is say, look, let's get all opinions, or rather options, on the table. Let's have everybody thinking about solutions rather than trying to deny the science that's so clear. Let's have everybody thinking about it so that, you know, maybe there's a solution that comes from a more conservative political viewpoint that should be talked about. At least then people have a voice at the table. What we can't afford to do is deny there's a problem, and there's a real problem. You know, there are people in our community who won't even advocate at that level to say, let's recognize that this is a problem. So we try to get out there and say, yes, it's a problem. Now let's talk about solutions, and get more people talking about it from their own angles. So that's what I try to do.
It's incredibly important for us to get all of us together who are listening here, to get our colleagues out there. I mean, just to ask them, do you care about climate change? And everyone, every scientist, there is, you know, no one will say, no, I don't care. It's not a problem. If they care, get out and talk about the science. Don't be an advocate if they don't want to be an advocate. Be an advocate if they do. But get out there and talk about the science. Because, you know, there are so many scientists who are just sitting in the lab, and, you know, who pays for our science? It's the public. There's a big problem. You got to get out and talk to the public. Mm-hmm. That's what they're paying for the science for, is to understand the nature of what's going on with our environment, and what good is it if we just put all our knowledge in journals and in databases.
Right. You know, you asked about what do you tell your family and friends about activities that you can do or actions that you can take. And we've talked about expensive things like, you know, oh, you know, you could buy an electric car, or you could put solar panels on your roof. These are great, and we do have to buy new cars now and then, so we probably will buy an electric car the next time we buy a car. But you can also do things like minimize your red meat consumption. That's huge, you know, and it's cheaper actually, you know. So you can do a lot of things that you can get on your bike, or you can walk, or, you know, take the stairs. All these are healthy things to do as well as cheaper things to do. So there's lots of ways that individuals can help.
And save money.
And save money.
Everyone likes to make fun of those LED light bulbs and those hybrid cars, but I'm saving a lot of money. Thank you.
No, that's great. It's especially nice to hear that. I appreciated hearing that, getting all the solutions out on the table and not having it be a bipartisan issue, and having those solutions being discussed, and also the economic opportunities that these bring too. So really appreciate it. And yes, there's space for climate science experts to be advocates as well as to present the science, and especially we need climate literacy and scientific literacy, and I really appreciated hearing the way that we can encourage others to give back by sharing that back with the communities. So we are out of time, but I just want to thank all of our speakers. Thank you so much. This was really a fun panel presentation, and really appreciated this. We've had lots of people write in and also thank you, and be asking about some of your resources, and so we'll follow up with each of you too, but thank you for our audience members for participating. If you have colleagues who are not able to attend this webinar, please let them know that it was recorded and will be on our website soon. We also do have some slide decks that we've been working on, one about climate proxies in general, and then also a case study with the drought in California. So we'll have those be sent out to our Climate Voices participants soon. And if you or your colleagues have not yet registered for Climate Voices but would like to become part of this network, please go to climatevoices.org and click on Become a Speaker. Thank you so much to the presenters and the audience members today.
Great to be here.
Thank you for organizing this. Nice to participate.
Thanks.